there are a number of reactions where electrons are transferred from one element to another. Those are called redox reactions, right? When electrons are transferred, one species oxidizes, which means it loses electrons, and another reduces, which means it gains electrons. And examples of that are simple replacement reactions, such as the one shown below. Zinc and copper nitrate is a single replacement where nitrate is replaced, or copper is replaced with zinc. Or or combustion reactions, anything that's oxidized, any combustion reaction where hydrocarbons are burned. And so you already should be able to figure out what the charges are of these elements, at least some of them, right? And those charges are going to be called oxidation numbers or oxidation states. Now, you've already heard me refer to when, for example, when zinc nitrate was mentioned, that the oxidation state of zinc is +2, and then I had to explain myself and say, well, that's, I meant charge, and so those are two not necessarily interchangeable, right? So if, for example, we have zinc by itself and it's a solid, it's a shiny metal, we know there are no electrons that have been given up yet. Okay, so it should have an oxidation number or a charge of 0. It's neutral. It still has its two valence electrons. And and then we know what the charge of copper is, just based on the fact that we know what nitrate is. Nitrate's -1. It's there twice, so we know this is copper 2 nitrate. So the charge of copper in copper nitrate is +2. And on the right side then, what happens is the copper here is reduced. Okay, it goes from +2 to 0. Right, so here now copper is by itself. So it now is 0. And zinc has oxidized. It now has a +2 oxidation state, right? It now is partnering with nitrate. And there's still 2, that means zinc is +2. So what's happening here, in order for zinc to go from 0 to +2, it must lose 2 electrons. Okay, so 2 electrons are lost from zinc, but they're taken up by copper. So copper has a +2 charge, and when it gains 2 electrons, it goes back to 0. Okay, all right, so the copper is reduced. Oxidation, loss of electrons. And so you can tell just by simply assigning oxidation states to some of the metals. You can also assign oxidation numbers to nitrogen and oxygen, but it's not necessary at this point because nitrate stays together and electrons are not transferred there. And so you cannot just have an oxidation reaction. If the electrons are lost, they have to go somewhere. They're going to be picked up by something else. Think of reduction as a reduction of the number here, right? +2 is lowered to 0 here, right? So that's a reduction. Okay. And so by definition, I didn't say it really out loud, is by an ion's charge or a hypothetical charge, right? So we can actually assign, this is a covalent compound here, as I mentioned, NO3. If we draw it out, it's going to look like that. And so we really don't have charges here, but we can call this there's a hypothetical charge that we can assign, as we will in a minute, and that helps us explain where electrons are coming and going from. Nitrogen is one of those examples. It can be +5 or +3. Okay, so in order for us to assign oxidation numbers and figure out where the electrons are flowing, we have to follow some rules. There are some obvious oxidation numbers we can assign, like we did on the previous reaction. We clearly knew that zinc as a metal, as by itself, an element by itself, is going to have an oxidation state of 0. So if I see zinc or iron or lithium by itself or with a phase label solid, that's going to be 0. Now, we also have diatomic atoms, right? So if you remember, there's H2 and O2, N2, and the halides do this, F2 and Cl2, Br2, and I2. Now these elements are not by themselves, but they are with themselves. That means that the oxidation number of all of these elements that are in diatomics bound to themselves is 0. So they fall into this category. If you see H2 gas or I2, which happens to be a solid, and Br2 happens to be a liquid, if you see that, the oxidation number of these is all 0. Cl2 gas, F2 gas, N2 gas. Okay, these are all 0. So elements by themselves have an oxidation number of 0. That's important. And all of the metals by themselves, or elements in general, gallium or whatever you want to pick from the periodic table. Monoatomic ions get the charge of the ion. Okay, and so I brought back up this table from chapter 4, which told us what the charges are, right? And so here the charges are equivalent to the oxidation numbers. If I have something like sodium fluoride, I know sodium is an ion. It will have a +1 charge. And I know fluoride is an ion. It will have a -1 charge. And it's monoatomic because it's a single element. So here we have, and so hydrogen will have a rule on its own here in a second, right? But it is +1 for the most part, unless it is, of course, as an element by itself. But so all of those, potassium, rubidium, if they are monoatomic, not as solids, with another, either a polyatomic ion or another monoatomic ion, a counter ion, an anion, then they get just these charges, right? Everything here is +2, and then we know +3, +2, and so that's clear cut, right? But also copper falls into this category too, right? But copper, then we don't know if it's copper +1 or copper +2. So there we don't know, right? But it still has a charge of its ion. But we might have to determine it by looking at what it's bound to, right? Okay, so then oxygen, except for when it's by itself, when it gets an oxidation number of 0, is 99 out of 100 times is going to be -2. So H2O, that oxygen is going to be -2. If it's in, let's say it's acidic acid, CH3CO2H, which is acidic acid, that oxygen is bound part of a compound. It is going to have a -2 charge. So oxygen is always going to be -2. There are some unique examples like peroxides. Hydrogen peroxide is H2O2. Here hydrogen is -1. We can actually figure that out by looking at Rule 4. Rule 4 says that hydrogen is always +1, except in binary compounds. Well, binary compounds is when you have, it's an unusual case when you have a metal bound to hydrogen, like calcium hydride, for example. And then it's called a hydride. So if it's called hydride, it is H-, but you must have it bound to a metal. By the way, these rules are on page 349. And again, that's something you're going to have to familiarize yourself so that you can identify redox reactions, oxidations, reductions, and communicate with me where those electrons are flowing. So when hydrogen is bound to a metal, calcium hydride, or you could have sodium hydride, then it's going to be an H-. But it's unusual. For the most part, it's going to be +1. Just as shown on the table here. Well, I crossed through it, but it was listed as +1 as a monoatomic ion. And so that would be true in HCl, or even here in this acidic acid. The hydrogens here are all going to be +1. And it's equally true for the hydrogen peroxide. So if that's true for hydrogen peroxide, and so we have 2 hydrogens in that, and they're each +1, that contributes to an overall +2 charge. Now, what I'm about to show you is the last rule, which is that the sum of all the individual elements in a polyatomic ion or a compound add up to its overall charge. So a compound is going to be 0. A polyatomic ion is going to be the charge of that. Make a long story short, I mean, this hydrogen peroxide overall doesn't have a charge. This is not a polyatomic ion. So all of the charges of the two hydrogens added up together and the two charges of the two atoms added up all together should equal 0. And if that's the case, and here we have +2, then the oxygen must be -1. Each oxygen, because 2 times -1 is -2. And +2 -2 equals 0, so here we could have figured that out. But peroxides, once again, we're not going to deal with them all that much. H2O2 is about the only thing that you might encounter in Chem 1. Hydrogen peroxide. There are other peroxides, but they're organic peroxides, and they're better left for organic chemistry when you take that hopefully in the fall. Halogens are a little tricky as well, right? Except for fluorine. Fluorine is always going to be -1. That's not a problem. But we have other halides can bind to oxygen or bind to themselves, to other halogens, right? We can have something like ClO3, for example. Or we can have ClBr3-. So those kinds of compounds, you can have a whole array of chlorine of charges. You can have +1 and -1 and +7 and +5, as we will see in a minute. And you can determine that, of course, by what it's bound to, and knowing that oxygen, in this case, we know that oxygen is always going to be -2, and then we know the overall charge, and we can figure out what that is. I'll do that in a second on a separate slide. This is a little trickier because by this rule, let's see what it actually says here. Except when combined with halogens above it and or oxygen. Okay, so there's one more thing that needs to be added. It has to be the central atom too. So if you draw the Lewis structure for this compound, you'll find there's Br, Br, lone pair, Br. So these outside Brs, they would have a -1 charge. So this rule also only applies to the central atom. Then the oxidation number of the chlorine inside is going to be different than -1. And here it's bound to oxygen. So we'll go look at that in a second. So here are a couple of examples. I mentioned already rule 6, basically compounds and ions. You just have to look at the sum, right? So we have individual components here. We have a copper ion, and we don't know what it is, although most of you probably do. And we have 2 chloride ions, and so the charge of this plus the charge of that is going to equal 0, right? Because overall these two make a neutral compound, and we know chloride is -1. And we know that because we have 2 chlorides here, that copper has to be +2. The other alternative is copper 1. And we know this back from naming that we do know some charges of ions, but others we don't, especially the transition metals. And that's for ionic compounds. But we also have covalent compounds, and then we don't really assign a charge. This is why we call it oxidation number, because there is a difference. Nitrogen has an oxidation number, so does oxygen in this compound, but it doesn't have a charge here, right? I mean, we say that oxygen has an oxidation number of -2, but it's not charged because it is actually bound to it's bound covalently, so there are no charges here, right? And then remember the formal charges, we can assign formal charges. So we have a plus and a -1 and a -1, but we don't have actual charges here. So those are called oxidation numbers. And the formal charges are also not equal to the oxidation states or numbers, right? So we know that oxygen is -2. This is, and I'm going to get rid of this charge here, right? Because now we are looking at, and we do know that overall this is -1 because of nitrate has that charge. So we know oxygen is -2, -2, -2, and so that adds up to -6. And if it's overall -1, then the nitrogen must be +5, right? Because +5 and -6 equals -1, right? So again, that's the sum of the individual atoms adds up to the overall charge, right? And so the sum here in these neutral ionic compounds is 0, and the sum in the polyatomic ions it really depends on the charge, on the overall charge of the polyatomic ion, right? So I hope that makes sense. So let's practice assigning oxidation numbers based on those rules. If you haven't memorized them, go crack that table open. 349, I believe. I don't remember now. But if I give you something like perchlorate, and you look at that, you need to assign oxidation numbers to what you can. You know the overall charge is minus, and you know each oxygen is -2. So that leads up to an overall -8 charge, which means that that chlorine in the center has to be +7. Okay? So, and we do the same thing here, except now we have a -6, so this is +5. -4, so this is +3, and then just minus must be +1, and then of course chloride by itself is -1. Look at the array of oxidation numbers that chlorine can have when it's bound either by itself or to oxygens here, right? So this is, by the way, it's highly reduced in here, right? So this chlorine, the chlorine was, in a way, it was oxidized, right? It would react it with oxygen as a neutral compound to be reduced, okay? I mean, to be oxidized, right? It lost a whole bunch of electrons. Okay, that was a good brain fart, but I'll continue anyway, and it'll all make more sense. Right now we're just assigning oxidation numbers. We'll continue doing that here, right? So again we have a -8, but because now we have a -2 charge, the chromium has to be +6. Nitrogen here, right, if we remember the rule, this is not bound. If hydrogen is bound to a metal, then it's -1, but it's not bound to a metal, so it's always +1, right? So we have a +4, but then overall +1, which means the nitrogen has to be +3. Sulfate, again, oxygen, this is not a peroxide. Both of these, sulfate and sulfite, we have -2. 4 times -2 is -8. Overall -2 charge means this is a +6, right? And then this is +4. You should practice that. If you didn't catch on to that very quickly, I highly recommend you practice assigning oxidation numbers and review the charges and those rules. The book has some excellent examples. Now, this is just a cleaner numbers, no big deal. Let's take a look at these redox reactions. Mentioned oxidation and reduction already. This reaction leaves out all of the counter ions and atoms and or potential polyatomic ions that are not involved in the electron transfer, right? So we have copper 0 here. It goes to +2, so it loses 2 electrons, right? So one of those electrons is going to be transferred to the silver. And there are 2 here, so the second electron is going to transfer to a second silver. This is why we need that 2 here, because silver has to be +1. Now, since silver gains that electron and turns into silver 0, it is the species that is reduced, right? So the oxidation is copper going to copper 2+. That's oxidation. Is a half reaction where there is a loss, and I have that written out as a half reaction, just focusing on copper. So you're going to produce electrons, whereas you need to pump electrons into silver plus, right? So in a way, I should have really drawn that this copper transfers the electron to this cation, which then, after it has gained the electron, forms a reduced metal and is back to its shiny self, right? Okay, so let's look at those half reactions, and that's important too, right? So we have copper that's going to kick out the electrons. So it's one of the products, right? Of course, we don't see that when we combine those 2 reactions. They're just lumped in together. But copper kicks out the electrons, and then silver picks them up. So here the electrons are part of the reactant, right? So silver plus 2 electrons gives us silver, right? And so if you do what we did with the counter ions, you can do the same thing here. If you write all this out, it'll look like above, and you will have plus 2 electrons on the left side here coming from which are needed here on the left side, but we also have 2 electrons on the product side plus 2 electrons. But if something is part of the products and the reactants, it falls out. So we don't really see that there are 2 electrons needed for this reaction. It's not shown. But here, if we draw the half reactions out, then we can see where the electrons are and how the electrons are flowing. Okay, and so the copper which is being oxidized helps reduce the silver. So the species that's being oxidized is the reducing agent, okay, causing the reduction, right? It's the copper that causes the reduction. It's the silver that causes the oxidation. I mean, these really work together in combination, in synergy here, or whatever, right? Okay, so let's take a look at one or two of these and figure out where the electrons are flowing, right? So any kind of combination reaction, 2 things going to 1 is going to be a redox reaction here. I don't have a phase label here, but we know that aluminum is by itself, and so it gets an oxidation number of 0. Here bromine is by itself. With itself, I should say, it's also going to have an oxidation number of 0. But we know in aluminum bromide that we have a plus 3 and a minus 1, right? Those are the oxidation numbers of the atoms in the product. And so we can easily identify that aluminum is oxidizing, right? It's aluminum that's going to aluminum plus 3 and 3 electrons. And so that must mean that bromine is reduced. And that's true because bromine goes from 0 to minus 1. So it gains those electrons. So we have, and I'm going to write it like that, bromine gains 1 electron to form bromide. Okay? And so in a way we need this 3 times. Right? We need 3 electrons because each aluminum gives up 3 electrons. But because this is diatomic, we can balance this reaction. We actually need 6 electrons total here, right? So we need this twice. But for now, let's just focus on assigning oxidation numbers and figuring out, okay, that's the oxidation. And this here is the reduction. All right. Okay, let's do one more and then take a little break. So first let's assign the oxidation numbers to all of the elements of this reaction here. Iron, because it's bound to oxygen. We know oxygen is -2, right? In fact, we know oxygen is -2 across the board, because none of those are peroxides. This is carbon monoxide, carbon dioxide, and this is iron oxide, iron 2 oxide, right? Well, which tells us that iron is +2. Here, the carbon can be anything from +4 to -4. So it's kind of a wild card. We always have to determine the oxidation number of carbon. But if it's bound to 1 oxygen, and they're in a 1-to-1 ratio here, this has to be +2. And then iron here is 0 because it's by itself. So we just figured out one of them, right? We figured out that iron going to iron 0, that's a reduction. So that's pretty simple. +2, it's gaining 2 electrons. And so coming over here to the other product, carbon dioxide, now we have 2 oxygens, so that's -4. And so this has to be +4. And so carbon is being oxidized here. That's the oxidation. it already lost 2 electrons, but it's going to lose 2 more when it binds to another oxygen here, right? So oxygen adding across carbon is oxidation here. But oxygen itself doesn't undergo anything. Oxygen stays -2. So the electrons are not transferred from the oxygen here. They're transferred from the carbon to the iron. Let's take a little break and then practice a few more when we come back.